Uh, it's a great pleasure to be here in this discussion meeting, which is in honor of Professor T.V. Ramakrishnan. And I'm really thankful to the organizers, although I got this invitation on the last moment to give this talk. But since it's a wonderful meeting and with a very good gathering, it's always an honor to present work in such meetings. So I'm going to talk about periodically driven quantum many-body systems in the first part of my talk, which which will be basically on periodically driven Hubbard model. I will show how a boring, very weakly interacting Hubbard model can also give rise to unconventional superconductivity, which is spin exchange mediated even at half filling because of the speciality of the drive that we are using. And if time persists, I will talk about the second part, which is about periodically driven Sherrington-Kirkpatrick model, which is completely beyond the theme of this conference. Only if time persists, I will share a few slides on it, and I will show how in a periodically driven Sherrington-Kirkpatrick model, one can actually get a very robust discrete time crystal phase. But before I go to my talk, I would like to say thanks to Professor T.V. Ramakrishnan for all the inspiration. So my first work on localization was with PVR, where my first student Sabyasachi was also involved. And it was a great learning experience for me as well as for my student. And it also motivated me later on to get involved in many body localization, because before this work, I was actually never thinking about many body localization. And then we were actually trying to understand if we add interactions in graphene along with disorder, what will happen. And then, but slowly we forgot about the graphene and we got more focused on many body localization. Uh, so before I go to my main talk, I would just like to flash two slides on my most recent work on many body localization, where we have tried to prove some exact relations between various norms of quantum coherence and IPR as a measure of localization. And so these relations are exact and are independent of the basis in which you measure IPR or quantum coherence. But the good thing about these exact inequalities is that they helped us in thinking about what one can do to quantum coherence of a system in the presence of disorder and interactions. So naively, one will think that if you have disorder and the system is trying to go towards the localized phase, the coherence of the system should decrease. But if you look at the coherence of subsystems, so suppose you divide your full system into two parts and look at the coherence of the subsystem, then the subsystem coherence actually increases as you increase the disorder strength. And this is very interesting and useful because, okay, so first, how do you understand that when the system is approaching towards the many body localized phase, the subsystem coherence can increase rather than decreasing? And this is because in the many body localized phase, if you consider a part of the system that is very weakly entangled with the rest of the system, and if the system is very weakly entangled, A is weakly entangled with B, then A will not lose its coherence also very easily because of the interaction with B. And that's what helps A in maintaining and enhancing its coherence as you increase the disorder strength. And this is very useful for superconducting qubit arrays, which always has disorder because of randomness in the Josephson energies. And so what our work shows is that even if the coherence, so there are many sources for loss of coherence, but if you look at the loss of coherence only because of coupling between the qubits themselves, then the randomness in Josephson energy can help in enhancing the coherence of at least a subsystem of qubits because of this combined effect of disorder and interaction. So these are some things which we are exploring, but now I will go back to my main talk, which is about periodically driven quantum many-body systems. So as all of you know, that many interesting things can be achieved if you drive quantum many-body systems periodically. For example, there are claims of getting transient superconductivity with mid-infrared femtosecond lasers on striped phase of cuprates. And it is also possible to get anomalous quantum Hall effect in graphene with the help of light, and also in 3D transition topological insulators. And in context of cold atom systems, it is possible to engineer many interesting models which are not easily available in real materials. For example, Haldane model can be simulated with the help of periodic drive in cold atom settings. And this is related to the second part of my talk, which shows that you can also get non-equilibrium phases in periodically driven systems, which are very interesting. For example, and one of that phase is the time crystal, where you can break spontaneously the time translational symmetry of the system. And these discrete time crystals have been seen in trapped ions, in diamond nitrogen vacancy centers, NMR systems, and even in superconducting qubits. So let me first talk mainly about the periodically driven Hubbard model, where I will show how one can get superconductivity at half filling. And here are the references. So the main goal is, we all know that you get superconductivity only when you dope the Mott insulator away from half filling. And the question is it ever possible to have superconductivity starting from Hubbard type models already at half filling? Okay, so in equilibrium setting, we could not think of this answer so easily, but I will provide you a non-equilibrium route to answer that question, that if you drive periodically driven, if you drive Hubbard model at half filling, it can be possible to have spin exchange mediated superconductivity even at half filling. So the system we start with is very simple. You have this single band Hubbard model, and this is the drive, which is basically acting on a bipartite lattice. And V is the amplitude of the drive, omega is the drive frequency, and then there is a phase difference on the two sublattices for this drive. And so the main point is that this drive will, close to the dynamical phasing point, induce strong correlations. It will also induce higher range hoppings, and which can frustrate the antiferromagnetic order and eventually helps in stabilizing the D-wave superconductivity if you consider it on a 2D square lattice. But before you go to the details of the results, the first thing one has to worry about is, like, what are the relevant drive parameters one needs to work with. Okay, so we all know that if you consider this time-dependent system in isolation and keep driving it periodically for a long time, then the system will keep absorbing heat and eventually go to an infinite ensemble state. But that's a boring state. So what are the right parameters where we can avoid that kind of heating? So it's well known that if you work in the high frequency regime of the drive, it can help you in suppressing heating, because the rate of absorption of energy by the system is actually exponentially small in the driving frequency. So the time it takes to heat up is actually exponentially large in the drive frequency. And this is also seen experimentally, where people have, this is the experimental picture from periodically driven Fermi-Hubbard model, where they basically looked at the double on occupancy in periodically driven Hubbard model and compared the double on occupancy with what one gets from the truncated Cloquet Hamiltonian. And what they have shown is that the truncated Hamiltonian one gets by truncation of the Magnus expansion almost acts like a quasi-conserved quantity for a very long time if the drive frequency is much larger than the energy scale involved in the undriven system. Further reduction of heating can be obtained if the drive amplitude is also large, and if you are in the beyond the linear response regime, because then one can again go back by doing a rotating wave approximation to the linear regime and show that the heating rate is further suppressed. So we basically looked at this periodically driven Hubbard model in the regime where the drive amplitude and the drive frequency both are much larger than the intrinsic energy scale of the undriven system. And we keep the ratio V by omega to be fixed. And now one can do the rotating wave approximation and keep all the effect of the drive into the nearest neighbor hopping, and all other terms in the Hamiltonian, that is the interaction and the chemical potential, remain time independent. And now if you do the Magnus expansion, and we have kept here terms up to 1 by omega, then in the zeroth order term, you see that the nearest neighbor hopping gets renormalized, and because of this effect of the drive, and this is basically the zeroth order Bessel function of first kind, whose argument v by omega also depends upon the phase of the drive. So at some special value of the phase, actually this hopping will become zero when you hit the zero of the Bessel function. We don't want to be really sitting at this dynamical freezing point, but if you are in the vicinity of the dynamical freezing point, then your nearest neighbor hopping is exponentially suppressed. And in unit of this nearest neighbor hopping, your effective electron-electron interactions will be highly enhanced. And if you look at the higher order terms induced by the drive also induces a second neighbor, staggered second neighbor hopping on each sublattice. It also gives a third neighbor hopping, which is also staggered. And the drive also induces a staggered potential. And then there is a correlated hopping, which is basically a spin-dependent hopping. And it prohibits doublons and holons to hop from one sublattice to another sublattice. So if you look at these higher order hoppings which are induced by the drive, because of their staggeredness, they don't break the particle hole symmetry. But when you go to the effective, T effective becoming very small, which also means that U effective and delta and all other parameters are very large, these higher order hoppings are still capable of frustrating the antiferromagnetic order in the half-filled system. U over T effective, yeah. So here is some of the parameters. So if you choose some very large amplitude and very large frequency, keeping the ratio to be 2.5, and just start with some weakly interacting Hubbard parameters, you see that the nearest neighbor hopping effectively goes down. Electron-electron repulsion and the staggered potential increases as you tune phi. This is the higher order hopping, higher range hopping, and this is the correlated hopping. So now you have a weird system where it's not only the strongly correlated Hubbard model at half filling, but you also have a equally large staggered potential. And in this system, it's not that the doublons will be projected out from all sides of your Hilbert space in the effective low energy Hamiltonian, but what will happen is because of the equally large staggered potential, that on one sublattice, holes are energetically expensive, and on the other sublattice, doublons are energetically expensive. And so one has to deal with different kind of harmonic operators on A and B sublattices, one which includes doublons but does not include holons, and the other one which includes holons but does not include doublons. And another interesting thing is because of this staggered, equally large staggered potential in this strongly correlated, effective strongly correlated Hubbard model that we get, some of the hoppings are still allowed. So for example, the one shown here in blue are still allowed because doublons on A sublattice and holons on B sublattice are energetically favorable objects. So this system has enough charge dynamics, even though the system is at half filling, and that is why one can think of stabilizing some of the conducting and superconducting phases in this system. And if you do a Schrieffer-Wolff transformation, this is the effective TT prime J model, which you will get, where all these terms, J prime and T prime terms, are basically induced by the drive. So you started with the weakly interacting Hubbard model, which is U of the order of T, and now you have next neighbor hoppings, which are staggered, induced by the drive. And these next neighbor hoppings also induces a next neighbor spin exchange term. So now if you solve this model, keeping track of all the Gutzwiller projections such that on one of the sublattice you project out only holons, and on the other sublattice you project out only doublons, what you see is that as you tune phi for a fixed set of drive parameters, on a square lattice, D wave superconductivity turns in for a range of phi, where the nearest neighbor hopping is large enough to frustrate the antiferromagnetic order. As you tune phi, this is the next neighbor hopping. So the next neighbor hopping actually decreases, and then the antiferromagnetic order gets frustrated. But the system doesn't immediately become an antiferromagnetic Mott insulator, although the overall system is at half filling because the density difference between the two sublattices is still finite. So it is an antiferromagnetic metal, and it's actually a very bad metal with very small electron. And yeah, yeah. So it's on a 2D square lattice. So this is actually a very bad metal with very small electron and hole pockets. And as you move from this point where the system has a transition from antiferromagnetic Mott insulator towards the superconductivity, these pockets become bigger and the density of the quasiparticles on the Fermi surface increases. And as you keep tuning phi, eventually, it almost becomes like a connected Fermi surface, and that's the point where the system starts showing superconductivity, D-wave superconductivity. So we look for only D-wave and extended S-wave, and D-wave looks to be more stable in this periodically driven system. And just to give you an idea of it's not that it is very sensitive to the special choice of drive parameters that we have looked at. One can actually work with various set of drive parameters. All of these are chosen keeping V by omega to be fixed such that we can easily be close to the dynamical freezing point. And in all the cases, you get a broad enough D wave superconductivity. And one can also drive the system in a different driving protocol, where rather than tuning the phase of the drive, one can actually fix the phase and just keep changing the drive amplitude and the frequency, keeping the ratio of the two to be fixed. For example, in this picture, so here the V is going all the way from 20 to 80s, and phi has been fixed to some value around 1. And you see that the D-wave pairing amplitude survives for a very broad range of the driving amplitude. So it's not that we have to always work with very large driving amplitude or very large driving frequency, but of course, larger is the driving amplitude and the frequency, the heating rate will be lower. So that is the benefit. And this is the staggered magnetization, which turns on at the point where the superconductivity has gone away. So this is basically my conclusion from the first part of the talk, where we have looked at periodically driven Hubbard model, which is just a weakly interacting Hubbard model at half filling to start with. The drive not only induces strong correlation, it also induces next neighbor hopping, second and third neighbor hopping, which is very crucial to frustrate the antiferromagnetic order. It also enhances the staggered potential to be large enough such that even though the overall system is at half filling, one sublattice is electron doped, the other sublattice is hole doped. And this basically favors conducting phases even at half filling in this system. And the frustration of antiferromagnetic order because of the drive-induced higher range hopping actually helps in stabilizing the D-wave superconductivity. So are there questions from this part? Then I can go to the next part. Shall I go to the next part? Okay, so this is on a very different topic. The only common thing is this is also a periodically driven system, but now we are not going to talk about any strong correlation physics here. This is mainly about the concept of discrete time crystal. Just like in a crystal, real crystal, we can break translational symmetry and have a crystal. Wilczek proposed long back that it should be possible to break time translational symmetry and get a time crystal, but that was proved. It was proved very soon that it's not possible to have breaking of time translational symmetry in a system which is in thermal equilibrium. But one can always look for non-equilibrium systems like these periodically driven systems where it is possible to have discrete time crystals and spontaneous breaking of discrete time translational symmetry. So what do I mean by breaking of discrete time translation symmetry in the discrete time crystal phase? So suppose your Hamiltonian has a period capital T. If you look at certain observable O at any time T, now this observable O may not have the periodicity of the Hamiltonian, but it may have periodicity of, say, some integer times the periodicity of the Hamiltonian. And this is what I mean by uh, breaking of discrete time translational symmetry. So these discrete time crystals have been seen long back in experiments, and Nico, when? 2017, okay, 8 years. Yeah, not long enough compared to the experimental papers which we have seen in this meeting. So discrete time crystals were proposed first in this experiment, a very interesting experiment on trapped ions, which basically simulates the system of interacting spin half particles. So the protocol is that you start with some random initial state of the spin half particles. In the first step of the drive, you flip all the spins. In the second step of the drive, you have evolved them with a Hamiltonian, which induces interaction between the spins. And the third step of the drive basically induces disorder into the system. It is a random magnetic field. So what you see here is that if there is no disorder in interactions, and if you just flip the spins, you only see a beating pattern. You don't see period doubling oscillations. If you add disorder but no interactions, then these beating oscillations also gets wiped out because of randomness in the field. Now, if you have disorder as well as interactions, when the system can be possibly in something called many-body localized phase, then you see period doubling oscillations in the magnetization, which is reflected in this subharmonic response in the Fourier transform of magnetization. And then if you make the epsilon very large, the whole thing goes away. So for certain value of the drive parameters, it is possible to have very robust period doubling oscillations which persist for a very long time. And this is not obvious. I mean, this is very different from what you will expect in any classical systems which have, or not even only in classical or in other quantum systems. Like, it's different from the normal oscillations one can expect because it's very robust against imperfections. Okay, so what are the minimal ingredients you need to realize a discrete time crystal? That there must be interaction between the basic degrees of freedom. You must have sufficient disorder in the system such that the system doesn't heat up when you drive it, because you don't want to drive it with a very high frequency or very high amplitude in this scenario. And then the system must be isolated from the environment. Okay, so that's why people thought that any system which is in many-body localized phase should, if you drive it periodically, will also give you a discrete time crystal phase. The question that I'm trying to answer in this talk is, if you have long-range random interactions, just having short-range random interactions, is it possible to have a discrete time crystal phase? Okay, because we know theoretically that people have seen disordered in short-range interacting disordered systems, a very robust DTC phase. So the question is, what happens in the long-range interacting systems? Of course, there are issues about stability of the ambial phase in the long-range interacting systems. And also, what we have seen is, if you have pure long-range interacting systems, you can only have pre-thermal DTC phase with a very strong initial state dependent. But does the situation improve when you have long-range interactions, as well as the interaction themselves are random? Okay, can we have a good DTC phase in this situation? And for that, we are basically looking at Sherrington-Kirkpatrick model, in which you have Ising spins, and all the spins are connected to themselves, and the random interactions are completely random, drawn from a Gaussian distribution with zero mean and standard deviation J. So now you can add, in this classical Sherrington-Kirkpatrick model, you can add quantum fluctuations, quantum dynamics, either with the help of a transverse field like here, or you can also add nearest neighbor hopping. So, I mean, nearest neighbor spin flip terms. So there are many ways to add quantum dynamics in this system. So we are going to study this quantum Sherrington-Kirkpatrick model in basically two periodic protocols. In the first protocol, we are in the first step of the drive, you just flip the spins. In the second step of the drive, you time evolve with respect to this quantum Sherrington-Kirkpatrick model, which has a transverse field. In the second protocol, the first step is same, that you just flip the spins. And in the second step of the drive, rather than having a transverse field, you have a nearest neighbor spin flip term. So let's first look at the first driving protocol, where you have a random transverse field. If you look at the correlation function time of this sigma z at any site I, what you see is that it shows period doubling oscillations, and which is also reflected in this subharmonic peak at omega by 2. And these oscillations actually survives up to large enough time. But then to further ensure that it really survives for even longer time, we look at the magnetization starting from a product state. And what you see is that after an initial rapid decay, which happens at a very short time, the magnetization shows plateau, and the length of this plateau in time increases exponentially when you increase the system size even by a small step. So this shows that these oscillations are really going to survive for a very long time in these systems. And if you calculate the DTC order parameter, you see that so this is the phase diagram for the DTC order parameter. In the JH plane, H is the strength of the random transverse field, J is the coupling from the SK model, and you see the regime in which the DTC phase survives actually matches very well where the delocalization to many-body localization transition happens in this periodically driven quantum Sherrington-Kirkpatrick model. So if you have larger strength of interactions, of course, you need the DTC phase survives for a broader range of the transverse field. Okay, so as you increase the strength of Sherrington-Kirkpatrick interactions, the range of transverse field for which your DTC order parameter is large is also large. And now we try to compare this case where you have the Sherrington-Kirkpatrick model, but it doesn't have the random transverse field, but the uniform transverse field. Okay, and you see that the regime in the JH plane, where the system shows a finite DTC order parameter, has reduced compared to the earlier case. So even though we have fully random all-to-all connected interactions between the spins, having randomness in the transverse field further helps the system to go into a broader DTC phase. And now we compare the case where you don't have the transverse field, but you are looking at the quantum Sherrington-Kirkpatrick model with a random spin flip term on the nearest neighbor bond. Now, this random spin flip term on the nearest neighbor bond are very interesting because for the time being, suppose you switch off this SK part and you look at only the random spin flip term on the nearest neighbor bond, you can map this to random hopping model of fermions. And we know that there are some interesting exact results available for this model, which tells you that this system actually can have localized states with anomalous behavior at the band center, where the localization length diverges at E equal to 0, and the density of state also diverges at E equal to 0. But now we have an interacting system we also have interactions between these spins on top of this random nearest neighbor hopping spin flip terms. So the question is is the randomness going to help in enhancing the Floquet MBL phase, or the randomness in the spin flip terms is acting against the Floquet MBL phase? Okay, so if you look at the delocalization to many-body localization transition in this periodically driven case with the random spin flip terms, it looks like the system remains many-body localized for a much larger strength of G. If you look at the static quantities, like entanglement entropy, or if you look at the level spacing ratio, it always remains Poissonian. But if you look at the dynamics, it looks like the system with the random spin flip terms actually starts becoming subdiffusive faster than the system which has transverse field. So we are a bit confused about like where actually that ambial transition or localized to diffusive transition is happening in this system. And now if you look at the spin-spin correlation in this system, of course, for short time, up to like 600 time steps or something, you do see very good period doubling oscillations, and you do see a reflection of it in the Fourier transform. But if you go to very long time, you see already at G equal to 0.4, you know, this, you start seeing the effect of initial states. Although for all the initial states that we have tried, you do see some period doubling oscillations, but the amplitude of oscillation starts shrinking as you go to larger and larger time. So it looks like the system is fully random, I mean, fully disordered, and both the ZZ interaction as well as the XY couplings are random. But somehow it has some signature of pre-thermal DTC phase in the sense that it has a strong initial state dependence once you go to values of G like beyond 0.2 or something. And it doesn't seem to be as robust a DTC phase as we found in the case of transverse field. So, and then you compare the whole thing with a system where you have long range interactions, but you don't have randomness in the interactions. Now the randomness is only in the transverse field or in your XY spin flip terms. So if you look at the case of, say, power law interactions with alpha equal to 1 with random transverse field, you see there is a very strong initial state dependence. So this is not a fully clean system. So this is not a standard pre-thermal DTC, which people see when you have purely clean long-range interacting system. You still have randomness through the transverse field, but the system does not show a good DTC phase. It has strong initial state dependence. And even in the case of XY couplings, it actually shows initial state dependence. So with this, I would like to conclude. So I think it's very important to have randomness in the spin interactions in order to have a robust GTC phase. And if these interactions are random as well as long range, that helps in having a broad DTC phase. But on the top of it, whether you have randomness in the transverse field or not, that also decides the width of the DTC phase. And we are a bit confused about what happens when you have random XY spin flip terms, because the Floquet-MBL transition is not so clearly, I mean, it's not easy to make a conclusive statement about the Floquet-MBL transition because of the limited system size. But it looks like up to short time, it's a very robust DTC phase. But when you go to larger time, then you start seeing the initial state dependence in this second driving protocol. Thank you.
Thank Arti for an exciting talk. So the session is now open for questions. Yes.
So the models that you're writing down, they're these infinite range interaction models. Per the standard lore, these should not actually have MBL in the thermodynamic limit, and therefore no DTC either.
Yeah,
So,
but it is random interaction. So the source of randomness and the coupling is the same. So if you start with like a random model and then add interactions which are long range, it should not have MBL, right?
yeah,
But
I
here
don't.
it's a model of spin class to start with.
Maybe let me ask, what's your argument for this model actually having MBL in the thermodynamic limit? Is it just numerics, or is there some analytic argument for that?
Well, this is fully numerics. Yeah.
I'll stop.
This excellent talk. I have one question that, can you just put a light on, is there any materials where this property can be seen?
Sorry?
Any materials?
Which
where
one,
this
the
property
first
can be
part
seen?
or the
Maybe I missed
second
it.
part?
Can you say?
Which one you are asking, the first part or
Maybe
the
this
second?
one actually.
The second part?
Yeah.
Well, you can try to look for something in cold atom systems, but I cannot suggest any real materials where it can be seen. But in cold atom systems, as I shown the first experimental result from 2017, that was also on spin systems, but the interactions were not all to all and they were not fully random. So it should be possible in some trapped ion systems or cold atoms.
Okay, thanks.
Any other question? If not, maybe I'll ask you one question. This is from the first part.
Yeah.
So you argued nicely that why the effective interaction will increase with periodic drive, right?
Yeah.
So the question is that after that you analyze this model using this effective hopping and etc. So those effective parameters, hopping, etc., are obtained using phase space argument, right?
They're obtained from the Magnus expansion.
Right. So,
Yeah.
so how valid that is when you have a time-dependent perturbation?
No, I didn't understand your question.
Okay, so the question, okay, let me ask.
So basically, let me just repeat what we did, right? So this is the effective Hamiltonian here that you can get if you do a truncation up to 1 by omega terms, right? So here you already have second neighbor hopping, third neighbor hopping, staggered potential, correlated hopping, and everything.
So now, can I consider this to be static?
Yeah, this is basically for all practical purposes is a static model.
This is
a static model, and that's what we solve.
Okay.
Yeah.
Okay. If there's no more question, let's thank Arti for this wonderful talk. And the patient concluded here, and we'll break for